two circles G1 and G2 intersect at 2 points M and N. Let AB be the line tangent to these circles at A and B respectively, so that M lies closer to AB than N. Let CD be the line parallel to AB and passing through the point M, with C on G1 and D on G2. Lines AC and BD intersect at point E. Lines AN and CD intersect at point P here. And lines BN and CD intersect at Q. And what we'd like to show is that EP is equal to EQ, that the two blue segments are equal. So how do we get started on this problem? Well, it definitely appears that PM is equal to MQ according to our diagram. So we conjecture that PM is equal to MQ. And if that were the case, then if PM were equal to MQ, then in order to finish the problem, we'd also like to have that angle EMP is equal to 90 degrees. Because if we can show that angle EMP is 90 degrees and PM is equal to MQ, then by the Pythagorean theorem, we'd be done. So now it just suffices to prove these two things. So let's go ahead and focus on proving that PM is equal to MQ first. Let's go ahead and ignore that real quick. So how do we go about proving that PM is equal to MQ? Well, suppose that M were the midpoint of PQ, then that means that since PQ is parallel to AB and AP and BQ intersect at a point N, that means that there's a homothenuse centered at N, mapping P to A and Q to B. So it's natural to see where it would send M. And indeed, it would send M to this point, suppose, X here. And by homotheny properties, we'd like to show that X is midpoint of, it is a midpoint of AB. This is what we've reduced to showing by taking that homothenity at N. But how do we go about showing that X is the midpoint of AB? Well, we have lengths and circles. So the best thing to do whenever we have lengths and circles is to try power of a point. And because we want to prove that AX is equal to XB, it seems natural to try using power of a point at point X. So if we use power of a point, we end up getting XA squared, because XA is tangent, is equal to XM times XN. However, XB squared is equal to XM times XN as well, by power of a point on G2. Therefore, XA squared is equal to XB squared, so XA is equal to XB. All right. So now we know that PM is equal to MQ. So we can go ahead and say that this is for sure the case. And now all that's left to do, I can go ahead and get rid of this line here. There we go. And all that's left to do now is to prove that angle EMP is equal to 90 degrees. So all we have to do now is show that angle EMP is equal to 90 degrees. So how do we go about proving this? Well, this is just equivalent to EM being perpendicular to CD. And this line CD seems kind of like nasty to deal with. So let's try dealing with AB, because AB is parallel to CD by definition. Then now we want to show that EM is perpendicular to AB. Well, now let's take a closer look at the relationship between E and M with respect to AB. And if we take a closer look, we might notice that E and M might be reflections across AB. So E and M are reflections. That's a possibility. So how do we prove that E and M are reflections across each other? Well, let's try seeing if there are any other lengths equal to AE or AM, because we'd like to prove that AE is equal to AM, because that would similarly mean that BE is equal to BM, which means that they are reflections. And so if EA is equal to EAM, let's see if there are any other lengths. And if we take a closer look, we see that AC is also equal to this. So we conjecture that EA is equal to AM is equal to AC. So let's try proving this one at a time. Let's first try to prove that AM is equal to AC. This is pretty much showing that triangle ACM is isosceles. In other words, we want to show that directed angle ACM is equal to directed angle CMA. But this should be straightforward because we have tangent lines and angles work well with tangent lines. In particular, directed angle BAM is equal to directed angle ACM because of the tangent circles. However, it is also equal to, because AB is parallel to CM, it is also equal to angle CMA, and therefore it's isosceles. Furthermore, since these two angles are equal, we know that angle EAB is equal to angle ECD, which is angle ACM. So it's also equal to angle EAB. So this angle and this angle are equal. So let me go ahead and draw that in. These two angles are equal. Similarly, these two angles are equal. And by ASA congruence, that means that these two triangles are congruent. And and consequently, that implies that EA is equal to AM and EB is equal to BM, and therefore M and E are reflections across each other. And we are done. And this is very similar to an AIME problem that I discussed earlier on this channel, specifically a problem from the 2023 AIME II that again involved this point E and the fact that EM is perpendicular to AB. This problem is not too different from that problem because the only other observation required is that PM is equal to MQ, which is pretty easy to see from a homothency centered at N. So thank you so much for watching this video. Please subscribe if you'd like to see more.